properties. And very scarily, now we're going to probably fall off the pace today because we took some time on homework, but that's okay. I looked at our schedule and we're like right on schedule. So that immediately shocked me and scared me at the same time. I've been having kind of a hell of a Tuesday morning until that point. Then I was like, wow, really? I'm on schedule? That's crazy. So hopefully we'll stay on schedule with the syllabus. And we're going to do that by starting to consider subsurface properties that are important for us as groundwater in order to understand groundwater. Okay, so we're gonna do a lot of these drawings in the future for the next little bit. And we're gonna think about a cube of porous media. So I spent all this time getting really good at drawing these cubes on the whiteboard. Now I'm having to learn to redo it on the computer pad. It's getting better, but it's still not perfect. Okay, so in our cube of porous media, we're going to have a bunch of sand grains. All right, and so you can draw them however you want, but these are sand grains. Okay, so this is my cube of porous media. All right, and here we're just going to consider some sediment. All right, and we call this porous media, all right, because it's full of two things: grains, all right, and these are generally, when we're talking about them, they're going to be sediment. Sand, clay, gravel, cobbles, whatever, all right, sediment. And in between the grains, we have pores. And this whole cube is porous media. Okay, when I When we pump groundwater, where does the water come from? Where's the water stored underground? Yeah, in the pore space. All right, so pore space. So when we look at sort of a, let's say that this cube is 1 meter. No, it's not. It's delta x by delta y by delta z, and we'll talk about those sizes here in a little bit. But when we're going to look for water or use water, it's coming out of the pore space. When water moves, so if I was to pump water and it would have to move through this porous media, how's the water move through this? Does it move through the grains? No, it moves around. So the water's got to move through the pore space, right? It's got to follow a path through pores. So the water moves through the pores. All right, so one of the things that we've got to start doing as hydrogeologists or anybody interested in subsurface reservoirs, oil and gas, water, air, whatever, all right, soil, we have to start thinking about things in a couple ways. First of all, we got the total volume of our porous media. What would the volume of this cube be? How would I calculate it? Yeah, delta x times delta y times delta z, right? All right, so that's the volume of my porous media. But if I wanted to know how much groundwater I had in this cube, I need to know the volume of what? The total volume of the cube or what? How would I know how much groundwater is in here? Yeah, Tanessa, just yell it out. Nobody's. Yeah, you'd need to know the pore volume, right? So the first and most fundamental property we're going to talk about is a property called porosity, all right? And porosity is the ratio of the volume of void space or pore space to the total volume of our REV. Porosity. And we're gonna use the symbol N for porosity. It gets called phi. It gets called a lot of different things in the literature. We'll stick with N in this class for the most part. But when you start reading hydrogeology papers, the Greek symbol phi is a very common symbol for porosity. But a lot of things get used. You got to start just reading what the symbols mean. We'll use N for porosity. And N is equal to the volume of the pore space or the volume of the voids over the total volume of my porous media. So this is our first fundamental property of the porous media. It tells us how much volume we have available to store water in the ground. So as an example, let's do a calculation. So let's do an example here. And let's say we are considering the river as it flows through the Hellgate Canyon. So this is Mount Sentinel and this is Mount Jumbo. All right, and the river flows down a pretty narrow valley here through the Hellgate. And I'll tell you a few things about this, about the Hellgate. The sediment, the alluvial sediment's about 10 meters deep in the Hellgate. And then the Hellgate Canyon is about 3 kilometers or 3,000 meters long. And it's about 300 meters wide. So I want to calculate the total volume of water stored in these alluvial sediments in the Hellgate Canyon. And I'm going to tell you that the porosity here is equal to 0.3. All right, so if we assume that the sediments are fully saturated, what do I mean by fully saturated? Yeah, all pore space is full of water. All right. Calculate the volume of water in Hellgate. All right, so everybody take a minute and see if you can make this calculation. And I'll just remind you that my definition of porosity is this. Okay. Anybody got a number for me? All right, how'd you do it, Finch? Was what, 9? And that gave me, what was it? Okay. Finch even thought about significant figures there and said it should be 3 times 10 to the 6th. It's probably true. Okay, so really easy, right? It's just the ratio of the two. It allows me to, porosity allows me to easily convert from pore volume to total volume or from total volume to pore volume. All right, it's a fundamental thing that we need to understand and think about. Okay, so porosity is not the same throughout the earth. All right, top gear, top tip. So what do you think controls? Well, let's first of all, let's just talk about some types of porosity. All right. So the first type that we discussed is what we call intragranular. And actually, I'm going to stop doing this 3D and just go to 2D so we can go faster. So now we're just looking at the front face of our cube, just to make our lives easier. All right, so the first type is the type we just talked about. That is called intragranular porosity. All right, and that is the space between grains. Right, so we got grains of sediment, and the intragranular porosity is the space between those grains. All right, another kind we can have is we could be up in the, let's say, up in the mountains or anywhere really, I guess. But we can have rock that has cracks or fractures in it. So this is intact rock. And these are fractures. And in the parlance, these are called fractures, and this intact rock is called matrix. All right. So if I look at this cube of fractured rock, I can also have fracture porosity. All right. And that would be the volume of the fractures to the volume of rock. All right. And then finally, another kind of porosity that we might have is, say, in volcanic rock or something like limestone. We can have intact rock, but there are large sort of spaces excavated in this rock. And in limestone, this can happen because of, we'll draw another bug down here. So if we're in limestone, these can be dissolution features. Um, and in volcanic rock, they could be gas bubbles, right? Right? And these are called vugs. Now, in both of fracture porosity and, say, in vuggy rocks, you have the fracture porosity, but then the matrix has can have intergranular porosity, all right? And we would call that matrix porosity. So these are the main types or areas where you could store fluids inside rocks. So the intergranular porosity in between grains, those can either be sediment grains, or there are, even in igneous rocks, there are very small spaces in between the crystal grains, all right? And those have porosity. But then you also have fractures and vugs, these openings, and those can be filled with water. Yeah, Tanessa. Yeah, they're like synonyms. We would matrix really refers to the sort of other porosity besides um, uh, fracture or vugs. So as an example, if I was in, say, our first example in the Hellgate alluvial aquifer, which is just sediments, it wouldn't make much sense to say matrix porosity, because you're not in unconsolidated sediments, you don't really have fractures. You've got just sediments. So we would call that intergranular porosity. We wouldn't say it's matrix. But in the mountain block, like up in the mountain block, say on Mount Sentinel, we have fractures. We've got fracture porosity. Those fractures run in sandstone, and that sandstone has intergranular or matrix porosity. Okay, let's that's a reasonable spot. Let's take a quick 5-minute break. Use the restroom if you need to. Go outside, whatever, and then we'll meet back here at 9:11. I'm gonna pause the recording. Okay, so let's start thinking about what affects porosity in the subsurface. So what do you think are some properties of the rock that might influence how much porosity we have? I'm going to put question marks there. We'll revisit that. You get Marco and I 3 beers in, and we'll have a real argument on this one. My argument's right though. You'll find out. Sorting. Does everybody here know what sorting means? All right, so sorting is how uniform are the grain size. For sure, this one is important. Okay, so what do we mean by type? So I think you're on a right track, but I wanna be a little more specific. What do you mean by type? Okay, so there's 2 things there. So what do we mean when we say clay or sand? What do we refer to? So one is size. I agree. But there's also another thing that's different between clay and sand. Yeah. So you're taking it a step further. So Jenna said something important. There's shape, right? So shape is really important. And Finch was onto something, that maybe it's harder to move through clays, and we're going to talk about that in a very rich detail probably tomorrow or on Thursday. But for sure, the shape of the grain determines how they can stack together, right? And so if they're, depending on whether they're spheres or whether they're plates or whether they're really angular, they're going to be able to stack together better. So shape is important. What else do you think might control the amount of porosity we have? Yeah. So, oh man, this is bad news. When this happens, usually it's really bad. I'm gonna quit OneNote and open it back up. Yeah, see, it wasn't even, that's all right. Shape, compaction. All right, so uncompacted, loose sediments, right? The grains are just kind of laying on top of each other. There's plenty of pore space. The grains can even move across or away from each other. But if the rock's been subject to a lot of lithostatic pressure and it's been compacted, porosity goes away. That's one of the things with diagenesis or rock formation. We take loose sediment and we compact it and we lose porosity. What else do you think? Yeah. So I'll put packing here, and this is really kind of a subset of shape and sorting, but we often lump it as a different process. Kind of shape and sorting. What else? Any other things you guys think might affect porosity? It's pretty hardcore, but we'll put it in here. All right, so these are forces. So minerals, are composed of all kinds of crazy crystals, and depending on how the atoms share their electrons, you get different charges on the surfaces. All right, and they can repel each other or attract each other. It's a minor player, but it can be important in clays. What else? There's some big ones that we're still missing. Yeah, so diagenesis, compaction, and cementation, right? When we cement a sandstone, what are we doing? We're filling pore space with another mineral that glues the grains together. So cementation is really important. Okay, so metamorphism does two things. It does compaction, it does cementation. It can also do mineral change, so you can grow crystals. So we could put that in there. Two other biggies. So I think a lot of what you guys are focusing on is intergranular porosity right now. Hint. Yeah, so structure, or I would say one important thing is the degree of fracturing, right? So how much stress or strain has the rock been put under? So fracturing. And this is a function of stress and strain. All right, so you can bet that rocks that have undergone a lot of stress and strain, like mountain blocks, right? They've got a lot of movement, they've got all kinds of stuff going on. They're often very fractured. Yeah, so weathering, in particular, chemical weathering. Or dissolution of minerals. All right, if I'm dissolving minerals, then I often open up pore space. I guess physical weathering, ice wedging, things like that often open up more. So we'll put physical weathering too. You know, ice wedging is a good way to create fractures. Okay, so these are the biggies. We can use our knowledge of geologic history and geology to come up with some kind of predictive idea of the porosity. All right. So got a few things to show. Just some examples of how these different factors affect porosity. So, and then I want to get to thinking about values of porosity. All right. Hopefully no one went into a seizure. Okay, so here are some of the things that we talked about. So cementation, right? We are taking a sand, all right, and in order to glue it together, we fill pore space with another mineral, often calcite, all right, and we reduce porosity, right? So cementation is really important. Sorting, all right. Well sorted material will always have higher porosity than poorly sorted material. The reason for that is if you're poorly sorted, you can fit small grains in between the bigger grains. All right, so sorting will always, poor sorting will always reduce the porosity. Fracturing, all right, the degree to which we have cracks in the rock, all right, we talked about that. That will, if we have more fractures, we have more fracture porosity. It's kind of a no-brainer. Here's another set of images. So this talks about a few of the other ones we talked about, like Jenna said, packing. So how these grains are sort of sorted. Now, in most geologic materials, they're what we call close packed. It's just the way it is. But you can see that how these spheres are sort of lined up with each other. They have different amounts of pore space. All right. Sorting, we talked about already. Grain shape. All right. So clays are generally really flat plates. And, you know, a sand is generally pretty rounded. All right. And so they can stack. They can have different packing and different stacking. All right. Um, let's see. This is just basically the same things we talked about. So sorting, if you have poorly sorted stuff, you can fill porosity between big grains with small grains. Um, cementation, the amount of dissolution. So in a limestone, if we have a lot of dissolution features, we can have pretty high porosity. And then if we, you know, metamorphose something, so if we take clay and we make a shale, all right, we'll have lower porosity. All right, so this next image is a CAT scan of a pore network. So what they've done is taken a sandstone, they've taken a CAT scan of it, and then they've isolated the pores. And I want to talk about a few things. So they've extracted all the sand grains, and what you're seeing here left behind is the pore space. All right. Some really important things for us that I want to talk about. So you can see these like sort of larger volumes, and then those are connected with we have these larger volumes, and they're sort of connected by these long thin tubes. You see that? All right, so these have important names. So this larger volume is a pore. And then the tube that connects the two pores, say here's a pore, here's a pore. This tube that connects the two pores is called a pore throat. So let me, oh, so we've got these volumes in between grains, which is a pore. And those grains are connected, or those pores are connected by a pore throat. And we've got a network. These things are, it's like kind of like a ganglion. You know, we got a bunch of pores, and we got a bunch of pore throats, and they're connected. These two things we're going to talk about a lot because they control different things for us. So most of the volume for storage is in the pores. But as we talk about what controls how water can move through these things, the pores aren't the limiter. The pore throats become more important. All right. So for storage, the pores are really important, but for fluid movement, pore throats. Okay, let's go back here. Avert your eyes, it's gonna flicker. All right. So pore throat network. The water's got to move through this string of like tubes and in between these larger pores. All right, let's start getting calibrated. I will fully expect you guys to be able to have some characteristic values of porosity in your head. All right. I'm not saying you have to memorize this table, but I should be able to say unconsolidated sand and you should have a representative value in your mind. All right. You need to be somewhat calibrated to these numbers. So let's talk about them. So in general, what did I do? In general, unconsolidated sand, silt, and clay is pretty uniform. All right, anywhere between 25 to 40% is common. Some clays, depending on some other properties, can be as high as 60%. I've never measured a porosity that high. All right, I would consider 40% really high. So bottom line, for unconsolidated sediments, like 30% porosity is not wrong. You're always pretty close at 30%. So just in your mind, when you walk out today and you look down at the soil, you're like, oh, 30% porosity. All right, done. You won't be horribly wrong. The soil's probably closer to 40% in most places I've measured it, but 30% isn't terrible. Remember, that's percent. So the porosity would be 0.3. I will post this table on Moodle, but anywhere between 20 and 30% for unconsolidated sediments is a good number to have in your mind. All right, so now if we take that sediment and we undergo diagenesis, we're going to compact it, we're going to cement it. All right, so we would expect it to be higher or lower than 30%. Lower, right? So let's look at it. Ranges, so for sandstone, between 5 and 30%. I've never measured a sandstone at 30%. All right. Siltstones between 20 and 40. Again, that's really high. I don't know. That's crazy. Limestones, this totally depends on the degree of fracturing. But I would say in general, for sedimentary rocks, 10% is a pretty good value. All right. A porosity of 0.1 or 10% void space is a reasonable value for sedimentary rocks, right? That aren't highly metamorphosed. Okay, so we talked about crystalline rocks. So like I said, even granites, in between the mineral grains, the crystals, there is porosity. All right. On the order, good numbers for porosity of intact crystalline granite are on the order of 1% to 0.1%. So porosities of 0.1, 0.01 to 0.001. Just as a rough order of magnitude, I would say if you thought of crystalline rocks as having a porosity of 1%, that's a reasonable number. All right, so you've got essentially crystalline rocks at 1%, sedimentary rocks at 10%, and sediments at 30%. Yeah, Finch. Yeah, why? Well, why do you think? Yeah, so physical weathering would cause fracturing. What else? Yeah. Does anybody know what grus is? Grus, Grus, is highly weathered granite. And you can go, like, you can drive over Lolo Pass on the Lochsaw and you get into like these road cuts that are grus, and it looks like granite, but you can literally go there and with your hand, you can just scoop it out. It's like sand. That chemical weathering has dissolved all of the biotites and micas, and so they're gone. So chemical weathering can dissolve minerals completely, and it opens up pore space. So that's what's happening with these granites and gabbros. They have these, you know, minerals that are really soluble at the Earth's surface in water. So it's whatever the retrograde Bowen reaction series is, but you know, certain minerals are much more soluble than others. For example, micas and biotites dissolve really easily. It leaves behind the quartz and the feldspars. And the same thing happens in gabbros. So gabbro is, if you don't know what gabbro is, it's basically, you know, an intrusive basalt, and it has a bunch of olivine in it. And olivine is really unstable around water; it dissolves. So the same thing. So that's chemical weathering, and in particular, chemical weathering of these, you know, fresh igneous rocks that have minerals that are really sensitive to water. Like a sandstone, all that's left is the stuff that's resistant to water, right? And so you don't really weather, you don't dissolve a lot in a sandstone, but you will in a granite. So great observation, good question, and weathering is the answer. So 30% for sediments, 10% for sedimentary rocks, 1% for intact crystalline rocks, knowing that the degree of weathering could change it completely, right? So highly weathered rocks, 30 to 40% again, right? Basically like sediments. So let's just take a moment to like calibrate ourselves. It's roughly 30% or less of the volume in the subsurface is available for water to be in. All right. And depending if we're in really intact rock, 1%. So if for those of you that watched the geosciences colloquium yesterday, and it was all about, um, you know, granite rock falls in Yosemite. I couldn't get the Tetons out of my head. In Yosemite, that super fresh, intact granite, the granite itself probably has a porosity of 1 to 0.1%. All right. If you added fractures, you're probably looking at something on the order of, a few percent. Okay. Porosity, general values. I'll post this, print it out, try and have these rough numbers in your head. If you know those, you're good. It's just a way for you to think about, well, A, get calibrated, and B, have some reasonable idea of what these porosities could be. If someone reports a 60% porosity, it could be true. It could be true, but you should be like, whoa, that's really high. That means over half of the total volume is pore space. That'd be a pretty crazy situation, of your rock to be mostly pore space. Happens, totally happens, but probably not very often. Yeah, so pumice can be very, very porous, right? It's basically just thin walls of rock, right? So those can be extremely high porosities, above 60%. But they're not that common, right? It would be weird. It would be a weird setting. Not that it can't happen, but that, if you see it, you should think, wow, that's high. That's really high. All right. So I want to escape out of here. Close your eyes. It's going to flicker. All right. Now we're going to do one final discussion on porosity, and that is on effective porosity. All right, and in order to think about effective porosity, I'm going to draw two cross sections, one of a sandstone all right, and so I've got these sand grains. And what's the kind of porosity in between the sand grains? Okay, I'd go 10%. This is reasonable. And what kind of porosity, what do we call this? Yeah, this would be intergranular porosity. All right, so 1, sand. And then 2, let's think about a pumice. And here in my pumice, what I have here is I've got gas bubbles inside a crystalline matrix. So this, so here my pore space surrounds the grains. And here my pore space is inside these gas vesicles. And I've got crystalline matrix surrounding those bubbles. So let's say that the total porosity N of these two is about the same. So we'll go with 10%. All right, so the volume of void space between these two rocks is the same. Now, there's a big difference in the pore networks here, right? So if I'm a hydrogeologist or whatever, some reservoir engineer in an oil patch, I am interested in the volume that's available for active fluid flow, right? And these pores here, they're isolated. There's no connection between these pores. So if I was to come in here and start pumping, say on this side of the rock, I might be able to evacuate one or two of these pores, but they're not connected. There's no travel path for the water between these pores. There's no way for water to move here between these pores, right? So pores are not connected. All right. Conversely, in my intergranular porosity, I have pores connected by pore throats. All right. And there's travel paths through this porosity. All right. And they're connected. So I could pump on one location in this porous media and water would be able to move through the porous media to my pump. So rocks can have the same porosity, but they don't behave the same. And as hydrogeologists, what we're actually interested in is the fluid behavior. And so we're interested in the volume of interconnected pore space. We don't necessarily care that there's all these vugs, all right, that are just out there because they essentially act like rock, like solid rock. So we are interested in the interconnected pore space. And so we have this idea of effective porosity. So effective porosity is defined as NE is equal to the volume of the pore of interconnected pores to the total volume of our REV. All right. And this is the void space that as hydrogeologists we're interested in for the most part. All right. It is the pores that are available for fluid to move. All right. So most of the time, we're going to use these as synonyms. But what, in all honesty, 99.9% of the time when we talk about porosity as hydrogeologists, what we mean is effective porosity, the interconnected pore space. All right. Okay, we're out of time for today. We will finish up just a few things on porosity and then start moving into some other properties on Thursday. Have a great rest of your week. Any questions before we go? All right, enjoy.